Topic today is complex ion formation and equilibrium. It's the last topic in our equilibrium chapter. And they're very interesting compounds. You can see the example here of hexaamine cobalt 3 chloride. And you have a cobalt with a 3 plus charge in the center of the complex. And then there are 6 NH3 groups that are complex to the cobalt ion. The cobalt ion would be the metal center, and then the NH3 groups are referred to as ligands. Some people say ligands, and it's that lone pair of electrons that donates into the d orbitals of the cobalt ion, and we're going to study that in detail a couple chapters down the road. But for now, because ammonia is neutral and cobalt has a 3 plus charge, then you see that there has to be 3 chloride ions to keep present in order to keep it neutral. Complex ions have beautiful colors, and you can see this kind of orangey yellow compound color. It's very beautiful. And the first scientist to study these compounds was Alfred Werner. He was a Swiss professor at the University of Zurich, and he won the Nobel Prize for his work in 1933 for this compound, structure of it, and other compounds related to it. So he's kind of the father of this field of complex ion formation. The geometry of the compound is octahedral. We studied that last semester. And you have 4 of those NH3 groups in a square plane, and then you have 1 ammonia above and 1 ammonia below that square plane in order to make the octahedral complex. So let's see what else. That's about it for the first slide. Okay, and then I wanted to show you how beautiful these colors are. This one is an iron 3 minus compound, which is complex with 3 potassiums. And these are called bidentate ligands. This is an oxalate molecule, or actually it's an oxalate. It's, hold on. C2O42 minus, which is oxalate, and there are 2 sites per molecule that bind into the iron 3 minus metal ion, and it's the lone pair electrons on the oxygens that donate into the d orbitals on the iron. So it's an interesting compound because of the bidentate nature of it. You get 2 ligands per molecule, and they kind of straddle that square plane in 2 instances, and it's kind of an unusual octahedral geometry for that system. Anyway, we make this compound at Cal State Northridge in the lab. The students love to make these green crystals, and you can see how beautiful they are. So I wanted to make a correction here. The iron is a 3 plus ion, and then you have 3 oxalates, each one being 2 minus. So if you want to look at the overall charge for the complex ion, it's going to be plus 3 from the iron plus 3 times -2, which is equal to -3. So I said earlier that the iron is -3. That's not true. The iron is plus 3, and then you get 3 of these 2 negatives to make -3 overall, which is what you see up here. Here's another example of a brightly colored compound. This one is copper 2 plus, which happens to have 6 water molecules that are ligands, and they donate their lone pair electrons from oxygen into the copper 2 plus ion d orbitals. So it's exactly the same. And then sulfate is the counter ion that keeps the substance neutral. And, you know, who knew that copper sulfate actually had all these water molecules hydrated to it? And in this unusual type of compound. And then these beautiful crystals come out of that. Another example here is cobalt 2+, and here's water molecules again that are ligands in this complex ion system. This one has this beautiful pink color, you can see from that test tube. And then two examples from nature, we find the chlorophyll system involves a magnesium at the center of this complex with this heme group. The red is going to be called, actually it's called porphyrin. And you have the lone pair electrons from the nitrogen that donate to the magnesium. It's a bit more complicated here, but there are two types of chlorophylls. Chlorophyll A has a methyl group, a CH3 group here, and chlorophyll B has a CHO. That would be a carbonyl oxygen there with hydrogen. And I showed this picture on the right-hand side to show you the beautiful green color associated with the magnesium complex. And we have the chlorophyll system contained within the plant cell chloroplast. So you have both A and B inside the chloroplast, and they're absorbing both blue and red light. Therefore, the color of the compound is going to be green. You could study the absorption spectrum to see that the absorption bands are for blue and red wavelengths. And then, of course, chlorophyll is associated with the pigment for photosynthesis. So the color of the green leaves in trees and plants is associated with this magnesium porphyrin complex ion system. And then finally we have the complex between iron 2, and if you notice, this is called heme complexing with it, but it's very similar to the porphyrin that we saw in the last slide. And this is going to be the components of hemoglobin, and hemoglobin is going to be colored differently depending on whether if there's oxygen present or not. And so when the hemoglobin group is oxygenated, you have oxygens that actually donate and become ligands. They donate into the iron 2d orbitals, and when doing so, they become beautifully colored. In this case, it's going to be that red color of blood. And a little comment here, poor blood and rich blood, I guess that would be the color. The second one would be the color of blood that's rich in oxygen. So in the absence of oxygen, you have the blue color. In the presence of oxygen, there's the red color. So you could read about this. There's a lot of detail associated with the number of oxygens that complex and so on, and certain diseases associated with it and so on. All right, and then now I'm just going to pick a very simple example to show you the equilibrium associated with these complex ion systems. So I will do some writing and we'll look at some equations here. So this is for complex ion equilibria. And we're going to look at silver plus aqueous. So that's going to be our metal. And we're going to have two NH3 groups. Those are going to be aqueous. So this is your metal. Metal ion. The ammonias are going to be the ligands. And then there's an equilibrium that forms between them to form the complex ion silver NH3 2+, and that's going to be aqueous. So this is the complex ion here. So we just pick a simple system. You just have two ligands. but we certainly could extend the analysis to more than two ligands. So when you mix silver ion with ammonia, there's a very high probability that the complex ion will form. And there's a number associated with that high probability. The equilibrium constant is Kf, and that's called the formation constant. And you can write the expression for Kf as the silver ammonia complex ion concentration divided by silver plus and divided by ammonia squared. Now this value happens to be equal to, for this system, 1.7 times 10 to the 7. So that is a very large number, and we expect the complex ion to form when the number is in high probability when the number is that large. So this is associated with a stable complex. It'll be in the form of the ion to the right of the equilibrium sign. So this happens to be a two-step process because there's two NH3 groups associated with it. And we can talk about the mechanism, which is one ammonia at a time. We start with the silver ion. I think I'll leave off the aqueous here just to keep it simple, but you do want to put it in. Silver plus the first NH3 is in equilibrium with the Ag NH3 complex ion, which is aqueous. Then that complex ion will continue along and pick up a second NH3 group to form Ag NH3 2, and it's still got a plus charge because ammonias are neutral, and it's the silver ion that's giving it the plus charge. Okay, so we have values for each one of these steps. We have Kf1, so this is the formation constant for the first step. That's 2.3 times 10 to the third. And then we have Kf2, which is 7.2 times 10 to the third. So they're about the same order of magnitude. The Kf2 is slightly more probable than the first. We can talk about the overall process here. So even though the silver ammonia complex ion with just one ammonia is present, in terms of the overall reaction, we don't include that. So we're going to say silver plus 2NH3 is in equilibrium to form silver ammonia complex with two ammonia molecules. So then we've talked about this before. You can write the Kf expression for the overall process. Whoops, hold on. And that's going to be equal to if you can add the reactions, you're going to multiply the equilibrium constants. So this is going to be Kf1 multiplied times Kf2. So then we would say 2.3 times 10 to the third, whoops, it's positive 3, sorry. 10 to the third times 7.2 times 10 to the third. And that's going to be the 1.7 times 10 to the 7 that I showed you before. Okay, so that's how that works. Now you can also kind of go through the exercise of writing the equilibrium constant expressions for each one of the steps, just to kind of play around with it and see how things work. you could say Kf is equal to Kf1 times Kf2, and we have Kf1 as the silver ammonia complex ion with just one ammonia, divided by silver plus and divided by ammonia. If we multiply that times Kf2, then it's silver ammonia complex with two ammonias. I know there's a name for that, but not sure about it. And then you're going to divide that by the silver NH3 plus with one ammonia, and then divide by NH3, like that. Okay, and when you do that, you can see, that, yep, the one with the one ammonia, that intermediate is going to cancel out, and then we're going to have that Kf for the overall reaction will be equal to silver NH3 2 plus ion divided by silver plus and NH3 squared. And that'll be equal to 1.7 times 10 to the 7. All right, the next step is to talk about the dissociation constant. This is going to be very important in biochemistry, by the way. Kd is going to be the dissociation. So there's a Kf and a Kd. And Kd is the dissociation constant. So you have the silver diammonia complex ion that has formed by reacting silver plus and ammonia, and NH3 2 plus aqueous is in equilibrium with silver plus, oops, I was leaving out the aqueous there, sorry, plus 2NH3. You see that? So this is the opposite of what we started with. If you scroll back up, you'll see that we started with reacting silver with two ammonia to form the silver diammonia complex, and this is the reverse of it. So in other words, if you mix together the silver and the ammonia to form the complex ion, that's kind of the stoichiometry part of it, right? But once the complex ion is formed, it'll go to equilibrium. And so we use Kd as the constant associated with that. Obviously, it will be the inverse of Kf. Oops. So Kd is defined as 1 over Kf, and this will be the silver ion concentration times ammonia squared divided by the complex ion. No, did I get that right? Yep, okay. Like this. And so that will be equal to 1 divided by 1.7 10 to the 7. And so that will be 5.9 times 10 to the 8. Okay, so Kd for this system is, minus 8, is small compared to Kf, which is large. All right, so that's pretty much it. Now we're just going to do one example where we use all this information, and we'll start that on the next part right here. Okay. So in this example, what is the concentration of silver ion if 0.01 molar silver nitrate, remember all nitrates are soluble, and 1 molar NH3 are reacted. So we're going to assume that when we mix those two things together that there's no volume change. So no volume change means moles equals molarity, because this is 1.0 liter for the solution. All right, and we're also given that Kf for AgNH3 2 plus equals 1.7 10 to the 7. Okay, so the question is, what's the concentration of the silver ion? And we can work that out pretty easily. Two-step process, just like we saw with the titration problems. First, you want to just take care of the stoichiometry. If we mix silver ion coming from the silver nitrate with ammonia, how much product is formed, and then we're going to let that product go to equilibrium. So it's going to be 2 steps there. So then let's start with the reaction of silver plus 2 NH3. Single-headed arrow, this is the formation, and that number is quite large, right? So it's going to be silver NH3 2 plus, and you can look at before the reaction, after the reaction. Before the reaction, you have 0.010 moles of silver and 1 mole of ammonia, and you start with 0 of the product. The reaction ensues. The silver ion is the limiting reactant. In this case, you're subtracting 2 times 0.01. And then you're forming here 0.01 for the product. So you get 0. Here you get 0.98 and then 0.01. Okay, now that's the reaction. Now the next step is to let the system go to equilibrium. So take the silver NH3 2 plus that's just formed. Now it will go to equilibrium to form silver plus 2 NH3, and this will be an ice table. You have moles equals molarity because it's 1 liter. The silver concentration is 0, and the ammonia here, you can think of that as like a, not a complex, not a common ion, but it's a common molecule in this case. 0.98 affects the equilibrium. So we'll look at losing x here, gaining x, and gaining 2x. So it's going to be 0.010 minus x, and 0.98 plus 2x. Then this is an example of dissociation of the complex ion. So we're going to need KD. KD. So KD is 1 over KF, and we had that number before. It was 5.9 10 to the minus 8. So 5.9 10 to the minus 8 will be equal to x divided by 0.98 plus 2x quantity squared, and then divided by 0.010 minus x. Okay, so we can look at the x in the denominator here and say, can we drop it? So we're going to take 0.01 divided by 10 to the minus 8. That's going to be around 10 to the 6, greater than 100. So it's okay to drop the x there. And similarly here on the top, you'd say that the 2x term is 0 because 0.98 divided by 10 to the minus 8 is going to be greater than 100 as well. All right, so then we rewrite it and say 5.9 10 to the minus 8 equals 0.98 squared times x divided by 0.01. Solve for x, and x is equal to 6.1 times 10 to the minus 10. Clean that up a little bit there. I made a bigger mess. Okay, so 10 to the minus 10. So go back to your table. What is x? X is equal to the silver plus ion concentration, and that was the question. What is the silver concentration? So silver plus is equal to x, 6.1 times 10 to the minus 10. That was the example, but you could also ask what the concentrations of the other things are. The ammonia here is going to be 0.98. Just forget about the 2x. And then the complex ion is still going to be approximately 0.01 because x is so small. So you could continue here and say the concentration of the NH3 is 0.98. And the concentration of the complex ion is approximately 0.010. So you could put little squiggles here, approximately, because some of it obviously has dissociated and formed silver and ammonia. So I think that's right. I believe that's going to be right, correct numbers there for the system. All right, thank you. That's the end of the discussion on complex ion equilibria. There'll be some other examples that are similar to this in your sapling, and you can look for some in the book as well. And there'll be a test question on this, I'm sure.